In the previous video, we began looking at how solar panels work, and in this video we're going to look at things in a little bit more detail. Now, the first thing to note is that a solar panel is made up of a number of solar cells, and in fact the correct name for a solar cell is a photovoltaic cell. So what we're looking at on the screen here is an image of a single photovoltaic cell. Now, the cell itself is made up of silicon, but we actually have two different types of silicon. We have what's known as an N-type silicon, and we have what's known as a P-type silicon. All the P and N stand for here is negative and positive, and we'll have a look at how these two types of silicon differ in a moment. Now, if you've ever looked at a PV cell in any detail, you'll notice that on the top surface we have a mesh as shown here, and on the bottom surface we have a sheet. And the explanation for this is relatively straightforward. On the top surface we need to allow sunlight to penetrate the silicon. So we need spaces within the metallic conductor to allow the sunlight to pass. Whereas on the bottom surface we don't have that need, therefore the bottom surface has a sheet rather than a mesh. And all we're doing there is providing a path for the electrons that leave the silicon semiconductor. Now, we'll talk about the silicon semiconductor a bit more in a moment, but basically what's going to happen is electrons are going to be knocked out of the N-type silicon. And because there'll be a deficit of electrons in the P-type silicon, the electrons want to pass from the N-type to the P-type. Now, as we'll see in a moment, they can't pass through the boundary between the N and P-type layers, so instead they have to find a new route, and the new route they take is around the outside. So they're going to travel here, they're going to travel around the circuit through the load. Providing there's a load there, the electrons will pass until they reach the P-type silicon. Now, the role of the sunlight there is to free the electrons so that they can travel around the circuit and through the load. Now, one of the challenges that this presents is that what we have here is DC current. The electrons can only flow in one direction, from N to P. And as you're probably aware by now, our national grid operates on AC currents or AC voltages. So what we need is to convert DC to AC. And the device that's used to do that is called an inverter. So in the next part of the video, we're going to look in a bit more detail at the semiconductor and how the N-type and P-type silicon interacts. And then we're going to look briefly at the role of an inverter and how it can convert DC to AC. So here we have a diagram of the cross-section of a solar cell or a PV cell. And on the left-hand side, we have our N-type silicon, and on the right-hand side, we have our P-type silicon. And just as a reminder, our sunlight approaches on the N-type silicon. That would represent the top surface. So the P-type represents the bottom surface. Now, as we mentioned earlier, our N-type silicon has a negative charge and our P-type silicon has a positive charge. And the way that that's achieved is through something called doping. Now, in the top right-hand corner, I've taken a couple of squares from the periodic table. And if you study the periodic table, then we know that carbon and silicon both have 4 electrons in their outer shell, whereas nitrogen and phosphorus both have 5 electrons, and boron only has 3 electrons. Now, because silicon has 4 electrons in its outer shell, what it forms is a crystalline structure of covalent bonds. So typically we would have silicons, and each silicon would connect to another 4 silicons. And now that silicon in the centre is stable because it has 4 electrons of its own, and it's also sharing 4 electrons with its neighbouring silicon atoms. But if we were to replace that silicon with a phosphorus as an example, which has 5 electrons in its outer shell, then we would get the following. We see our phosphorus in the centre and it's forming 4 covalent bonds, but recall that phosphorus had 5 electrons to begin with, so it's going to supply 1 to this pair, 1 to this pair one to this pair and one to this pair, but it's going to have one electron left over. Now that free electron is going to be free to roam anywhere in the lattice of that material. So if we refer to our diagram on the left, the N-type silicon is phosphorus doped. Let's just write P doped. And because it's P doped, we end up with free electrons throughout the N-type silicon. Now, if we were to dope the silicon with boron instead, then we would get the following. So in this diagram, boron only has 3 electrons in its outer shell. So it shares one with this silicon, one with this silicon, and one with this silicon. But we can see the silicon at the top is missing an electron. And in actual fact, that silicon is going to be desperate to gain an electron because at present it only has 7 electrons in its outer shell. The reason it has 7 is because it will have its own pairs of covalent bonds. Now the reason I've marked that with an H is because H represents hole. What we think of is free electrons and holes where electrons belong. So in actual fact, when the silicon is doped with boron, so B doped, what we end up with is these holes which want to accept electrons. So let's represent that on our diagram. We have holes throughout our P-type silicon. Now for completeness, we're going to discuss briefly how these two layers interact. But this is something you'll look at in more depth if you study the Electrical and Electronic Principles unit with us. But just to summarise, electrons and holes want to combine. And that's exactly what they do. What we get is we get electrons crossing the boundary and combining with holes, and we get holes crossing the boundary and combining with electrons. Now electrons, as we know, have a negative charge, and holes actually have an equivalent positive charge. So if holes are moving left and electrons are moving right, what we end up with is a certain amount of positive charge moving to the left and a certain amount of negative charge moving to the right. And the way that these would position themselves is close to our boundary. So we would end up with positive charges at the boundary of our N-type silicon and negative charges at the boundary of our P-type silicon. Now the significance of this is there'll come a point when electrons and holes can no longer travel across that boundary. And that will be due to these electrostatic charges that we now see at that boundary. Now because some of our electrons and holes have combined, there'll no longer be as many electrons and holes on either side of the N-type and P-type silicon. So let's simplify our diagram. And this region close to the boundary is called the depletion region. So this here is the depletion region. So the important thing about our depletion region is that the electrons on the left-hand side can no longer cross that boundary because negatives repel. If this electron moves close this way, it's going to be repelled by the electric field. And the same is going to be true for the holes. If the hole tries to cross the boundary, it's going to be repelled by the positive field. So it's no longer an option for electrons and holes to cross that boundary, even though the electrons want to get to the right-hand side and the holes want to get to the left-hand side. Now back to our sunlight, which is striking our N-type silicon, and in doing so, it's dislodging more of these electrons. So in actual fact, we end up with an abundance of electrons on the left-hand side, all wishing to get to the right-hand side. And here's where our circuit connection comes into play. Because by connecting our N-type to our P-type via an external load, it's going to look something like this. We've now provided a path for those electrons. So this is why we end up with a DC current from PV cells and therefore from solar panels. Okay, so finally, let's look at how we convert that DC current into an AC current. Okay, so what we're going to look at here is very much a simplification of a component called an inverter. And an inverter is used to convert DC to AC as it travels through a load. Now if we start on the left hand side, what we have drawn is exactly what we saw on the previous slide. We have our silicon with N-type negative layers and P-type positive layers. And when the sunlight strikes the N-type silicon, it releases electrons which need to travel round our circuit. The electrons travel from N-type to P-type, but they have to follow the direction around the outside for the reasons we spoke about before. So the electrons always travel in the same direction, from N-type to P-type. Now on the right hand side we have the same circuit but modified to include an inverter. Now the first thing I want to draw your attention to is the direction of the electrons into and out of the solar panel remains unchanged. So we still have N-type silicon and P-type silicon, and we still have electrons leaving the N-type and returning to the P-type. That has to remain constant because the flow of electrons through the solar cell can only happen in one direction. But what we're interested in is the direction of flow through the resistor. And here we have our load resistor, R subscript L. Now if we ignore the dashed circuit for the time being, what we can see is that providing our two blue switches are closed, the electrons are going to travel around the circuit in this direction. They're going to travel through the load in this direction, and they're going to rejoin the circuit in this direction here. So with the blue switches closed, in actual fact what we have is exactly the same configuration that we have on the left hand side. But what happens when the blue switch is open and the orange switches close? Well, now we can see that the blue switches are open and the orange switches are closed. So our electrons are going to leave the N-type silicon travelling in this direction, but they can't travel down this path here. There's nowhere for those electrons to flow. So instead, they travel in this direction. They can travel in this direction because the orange switch is closed, and they get to this point here. Now for the same reason, those electrons can't travel downwards because the blue switch is open. So they must travel in this direction here. So note that the direction of flow through the load resistor is now different. It's the opposite direction. The electrons will then continue around the circuit, rejoining the main circuit and flowing into the P-type silicon. Now the reason this is a simplification is because the types of switches that are used in an inverter are high precision IGBT switches. They need to be able to open and close very, very rapidly and with a very high degree of accuracy in order to provide us with our smooth AC output. But for the purposes of this video, we know that if we generate electricity using photovoltaic cells or solar panels, then the output must be connected to an inverter before that power is supplied to the national grid.